start. So we'll be doing applications of derivatives, and the prerequisite to this chapter is basically differentiation, basic differentiation, all kinds of derivatives of different functions. Of course, you need to know limits and continuity and differentiability. So there's 5 basic parts of this chapter that we will be doing. Those are tangent and normal. Next part will be the angle between two curves. So when you have two curves intersecting each other, the angle at which the tangents intersect at the point of intersection, that's basically the angle between the curves. And the next part is length of the tangent, the normal, the subtangent, and the subnormal. Subtangent and subnormal are just the projections of the tangent and normal on the x-axis. Next part is this derivative dy by dx as a rate measure. So for example, velocity is just a rate of change of displacement, acceleration is a rate of change of velocity. So dy by dx as a rate measure. The next part is errors and approximations. There is Rolle's theorem and Lagrange's mean value theorem, and the last two are actually very similar, as we'll see when we proceed. Okay, so getting to tangents and normal, we know that if we have any curve and we know a certain point on the curve x1 comma y1, and I take the tangent at this point, say, now the slope of this tangent is basically dy by dx x1 comma y1, where x is equal to x1 and y is equal to y1. So how will I get the equation of this tangent? It's quite simple. You can just write it as, basically I know the point x1, y1, and I know the slope dy by dx. So the equation of the tangent is just y minus y1 equal to dy by dx times x minus x1. So this is the equation of the tangent, and from this you can get the equation of the normal as well, which will be y minus y1 equal to minus dx by dy, negative of the reciprocal of the slope of tangent, times x minus x1. So this is the equation of tangent. This is the equation of the normal. It's simple. You basically have a point and you know the slope. Dy by dx represents the slope, and you know the point x1, y1. So this is how you get the equation of any line given a point and the slope. Dy by dx is basically your m. If you want to write it as y minus y1 equals m x minus x1, that's how you get this equation, dy by dx. So dy by dx represents the slope of the tangent at that point. So you have dy by dx there, and for normal you have minus dx by dy, which is 1 minus 1 by dy by dx. There's two main kinds of problems that are asked in integers. Those are regarding the slope itself, just the slope, and the other kind of question is in which you'll require the whole equation of the tangent or normal. Okay, so there's not a lot of new theory in this chapter. Whatever there is in the tangent and normal part, you already know that dy by dx is slope and how to get the equation of a tangent if you know a point. So we'll just proceed with questions. Let's start with this question. Find the sum of the intercepts on the axis of coordinates by any tangent to this given curve. Root x plus root y is equal to 2. So what we have to do is, at any given point x1, y1, we have to determine the equation of the tangent, and in that equation we have to basically identify the intercepts. How we do that is just by substituting the value of x as 0 first and then y as 0, get both the y and x intercepts respectively, and then see if that comes out to any interesting value. So first I'll differentiate this given curve. I have d of root x by dx plus d of root y by dy into dy by dx. This is basically the derivative of root y with respect to x, and this part is constant, so it will become 0. So what I have is 1 by 2 root x plus 1 by 2 root y dy by dx is equal to 0. This gives me the derivative. So now I have the derivative in terms of x and y. Basically dy by dx will be equal to minus root y by x. So I got dy by dx. Now I can write down the equation of the tangent in terms of any point x1 comma y1 which lies on the curve. So if I take this equation of tangent written over here and write it down, I'm just proceeding over here. So that is basically y minus y1 equals dy by dx into x minus x1, where dy by dx over here, if I'm considering the point x1 comma y1, is basically root of y1 by x1. So this is my dy by dx or slope at the point x1 comma y1, and times x minus x1. So we got the equation of the tangent. This is the equation of the tangent. Now we just need to find the intercepts. So to get the intercepts, I'll first get the y-intercept, meaning that x has to be equal to 0. So where the curve cuts the y-axis, I substitute x as 0. So do note that this x1 and y1 are the points on the curve. So these are constants actually, I can't replace them. Constants meaning for a specific tangent they are constants, otherwise they do represent any point on the curve. Over here I want to find the intercepts of the tangent, so I'll substitute this variable x over here as 0 to get the y-intercept. I have y minus y1. So since x is 0, I just have root y1 by x1 into minus x1. So that gives me minus root x1 y1, giving me the y coordinate as I'm so sorry, there's a minus sign over here. So the slope we got is minus root y by x. You have minus root y1 by x1. So this minus and this minus combines, you get a plus. You have y is equal to y1 plus root x1 y1. If I do the same thing to get the x-intercept, I'll have to substitute y is equal to 0. I can take y1, or I can take this expression dy by dx to the other side and then x1 to the other side. I'll basically get x equals under root x1 y1 plus x1. Alright, it's not too hard to see this also. How I get this is basically I have 0 minus y1. I'm substituting 0 because now I'm getting the x-intercept, so the y coordinate is 0. 0 minus y1 equals under root y1 by x1 minus sign over here times x minus x1. So this is basically minus y1 into under root minus under root x1 by y1. Just took it to the other side. This is equal to x minus x1. So this basically gives me the minus and minus becomes a plus. I have plus under root x1 y1 plus x1, taking x1 to the other side, gives me my x-intercept. So this is my x-intercept. I'll call this xc. This is my y-intercept, yc. Yeah, so I have x-intercept, I have y-intercept. Now I have to find the sum of the intercepts. That is basically xc plus yc. This equals, if I add both the equations, if this is equation 2, this is equation 1. If I add both the equations, I basically get xc plus yc is equal to x1. So root x1 y1 and root x1 y1 over here will combine to give you 2 root x1 y1 plus y1, which can be written as root x1 plus root y1 whole square. And since this point, this x1 y1 lies on the curve root x plus root y is equal to 2, this term is just 2. So it's just 2 square, which is equal to 4. The answer to this question is 4. Sum of the intercepts turns out to be a constant. So just one thing to note about the given curve. If you're given, say, a curve x square plus y square is a constant, you know that it's a circle centered at origin. It's a circle centered at origin. If you're given x power 1 plus y power 1 is c, this is a linear equation, so this is just a straight line. So straight line passing through x and y intercept c. Okay, so if I increase the power, if I go from x power 1 to x power 2 to x power 3, it curves this way, more outwards, you can say, like this. So if I have a power of x less than 1, what happens is the curve starts curving inwards. So you can actually even picture the graph of this given curve, root x plus root y equal to 2. Basically, if you have square, the curve is like this outwards. If you have a linear equation, it's a straight line. If you have a power of x less than 1, like root x, it curves inwards. So this curve will actually, first of all, we know that this curve has a root x and root y term, so it cannot exist for negative x and negative y, because under root of x and under root of y can only be positive. So this curve only exists in the first quadrant, and we know that its curvature is somewhat like this, more inwards than a linear, than a line itself. So the curve actually looks something like this. Okay. So another thing to note about this question is you can also use parametric form over here. If you take root x as 2 sine square theta and root y as 2 cos square theta, you will basically get this equation is satisfied by this parametric form, where you take the variable theta and you can proceed and you will still get the same answer. So let's look at another question, again on tangents. Show that the angle between the tangents at any point P and the line joining P and the origin is the same at all points on the curve. Natural log of x square plus y square is equal to c tan inverse y by x. So what the question is, we'll just make a rough diagram of the question. Basically we have to show that, say if you have a curve, the angle between the tangent at any point, if say this is the point P, and the line joining P and the origin, so say this angle or this angle, it doesn't matter, you have to show that that angle is constant, meaning that it's independent of x and y. So even if I move along the curve and I draw the tangent at a different point, join that with the origin, that point with the origin, draw the line, and then take the angle between tangent and the line joining P and origin O, that should be a constant. Okay, so let's see how we're going to approach this. So first we find out the slope of we basically require the slope of the tangent at the point. If we take, say, coordinates x comma y, so let P basically be x comma y. Okay, we're going to take this point and we're going to find the slope at this point. So slope is basically dy by dx. I'll just have to differentiate my given equation. So let's start differentiating this. So the left hand side, derivative of the left hand side, 1 by x square plus y square, that is the derivative of log of x square plus y square by d of x square plus y square. Now using chain rule, I get 2x plus 2y y dash. So I'm writing dy by dx as y dash. This is what I get on one side. So this 1 by x square plus y square I get by differentiating ln of x square plus y square with respect to x square plus y square. And then I have to differentiate x square plus y square with respect to x. So I get my dy by dx, which is y dash. The other side, now derivative of tan inverse y by x is 1 by 1 plus y square by x square. And again by chain rule, I need to differentiate y by x. So that is y dash x minus y divided by x square. Okay, so this, you should know how you get this. So basically, derivative of tan inverse x is 1 by 1 plus x square. So this is that variable inside tan inverse. Okay, and then by chain rule I need to differentiate y by x with respect to x after that, and that is by the quotient rule. You get y dash x minus y by x square. Okay, so let's simplify this. You get 2x plus 2y y dash by x square plus y square is equal to, so if I take LCM over here on this side, I'll get x square plus y square. There's an x square in the denominator over here, and x square over here as well, which will cancel out. What I'll get is y dash x minus y divided by x square plus y square. So the denominator will simply cancel out. This is what I'll get after I differentiate both sides. If you want, you can pause the video and try doing it on your own, because I've skipped some steps over here. Yeah, now if I cancel out the denominator, what I'll get is so since I want to get one expression just for y dash, which is dy by dx, I'll take all y dash terms to one side and take that common. You have 2x plus y equals y dash x minus 2y, which means that y dash is basically 2x plus y by x minus 2y. So I got my dy by dx. This is the slope of that curve at the point P, which is x comma y. Now what will be the slope of the line joining O and P? If you have P as x comma y, the line joining origin and P will basically be, let's call it slope y minus 0 by x minus 0, because origin is 0 comma 0, so that's y by x. So this is the slope of the line joining O and P, and I have the slope of the tangent at the point. Now I have to compare the angle between these two lines, the tangent and the line joining O and P. I get that by, so that angle is basically given by tan inverse mod m1 minus m2 by 1 plus m1 m2. That's the formula for angle between two lines, m1 minus m2, where m1 and m2 are the slopes of the lines, divided by 1 plus m1 m2. Okay, so I've forgotten the factor of c over here. Everything is multiplied by c into c into c into c here, yc over here, and cx over here, cyc. Okay, m1 over here is nothing but y dash, m2 is y by x. So I have 2x plus cy by cx minus 2y. I have this minus y by x, whole thing divided by 1 plus 2x plus cy by cx minus 2y into y by x. 2x square plus cxy, taking LCM just for the numerator, minus cxy plus 2y square. This will cancel. Then the thing is, my denominator will cancel. Denominator of both the numerator and the denominator, meaning this part, cx minus 2y and x, over here cx minus 2y and x. Once I've taken LCM, they are the same thing, right? So both those will cancel. So I can just ignore that. I'm just going to write this part, basically the numerator of the denominator. So I have cx square minus 2xy plus 2xy plus cy square. Okay, and over here 2xy will cancel. So finally what I have is 2 times x square plus y square by c times x square plus y square, which will cancel. So I just have to by c, and the whole thing has a mod. So the whole thing has a mod here, it has a mod here, so the mod here. The angle I get is tan inverse 2 by c, which is independent of x and y. So this angle is going to be constant no matter what value I take for x and y. Let's recap the question once again. So we have this equation of the curve given, ln x square plus y square is equal to c tan inverse y by x, and it's given that I need to show that the angle between the tangent at any point to this curve and the line joining origin and that point, that same point at which I take the tangent, the line joining origin and that point P is a constant. That's what I need to show. So to do that, I get the slope of both the line joining origin and P and the tangent at P. So the tangent at P is nothing but dy by dx, which is why I differentiated everything and got everything in terms of y dash, which is dy by dx. And the slope of the other line joining O and P, is basically just y by x. The angle between two lines is given by tan inverse m1 minus m2 by 1 plus m1 m2, where m1 and m2 are the slopes of the two given lines. Every question is different in this topic. There is no set rule as such. You have to try to picture what's happening in the question and convert sentences to equations, that's all. Continuing with application of derivatives, we'll move on to the next part of tangent and normal, which is the length of the tangent, length of the normal, and length of subtangent and subnormal. So say we're given a curve like this, the one I've just drawn over here, any rough curve, and I take a point x1 comma y1, point over here x1 comma y1. This, you can see this is the intersection of these two lines and the curve. Okay, so the first line I've drawn is basically the tangent to that curve at x1 comma y1, and the second one is a normal at that point. Now the length of the tangent mentioned in any question is basically this distance x1 comma y1, distance of this point from the distance of the point where the tangent intersects the x-axis. So this point, let's call this x c comma 0. So the distance between these 2 points x1 comma y1 and xc comma 0, this is the x-intercept, is basically the length of the tangent. Similarly, the distance between the point x1 comma y1 and where the normal intersects the x-axis, let's call this xc dash comma 0. This entire distance is the length of the normal. The subtangent is basically the projection of this tangent, the distance between x1, y1 and xc0 on the x-axis. So that is basically this distance. This is our subtangent, and the distance is nothing but the difference between x1 and xc. You can see that this point is x1 comma 0. So the length of the subtangent is xc minus x1 mod. Similarly, subnormal is the projection of the length of the normal, or the entire distance from x1 y1 to xc dash comma 0 over here, projected on the x-axis. That is the subnormal. So this is the subnormal. Okay, now that we've defined them, let's try to get the length of all 4 of these things. So I'll start with deriving the length of the tangent, length of the tangent. What is the equation of the tangent? As mentioned before, the equation of the tangent is nothing but y minus y1 equal to dy by dx at x1 comma y1 into x minus x1. Let's write dy by dx as slope m. So dy by dx at x1 y1, I'm going to write this as m. So what does that make the slope of the normal? Slope of the normal is nothing but reciprocal, negative of reciprocal of this. So this is slope of tangent. And minus 1 by m, which you can say is minus dx by dy, is slope of normal. Okay. Now that we have the equation, let's try to get this distance between x1, y1 and x-intercept of the tangent. Alright, how will I get this distance? Now, you can see that I have a right angle triangle. Let's take the points as P, Q and R. Now P, Q, R over here is a right angle triangle. So what I want is a distance PR. PR square is PQ square plus QR square. PQ is nothing but y1, which is the vertical distance of this point from the x-axis, the point x1, y1. So PQ is nothing but y1. So this is equal to y1 square plus QR square. How do I get QR now? So to get the point xc comma 0, so to get the x-intercept of the tangent, basically I'll have to substitute y equal to 0 in this equation of tangent. Why do I have to substitute y equal to 0? Because the y coordinate at the x-intercept is 0. So what I'll get is 0 minus y1 equals m. I'm writing dy by dx slope as m, x minus x1. Alright, which means that minus y1 and what I want is this x. So I'm looking to find out this x. Why this one? Because this is my variable in the equation of the tangent. Points x1 and y1 are already given, they are fixed. What I want is the value of this x. This is basically xc. So I have mx1 minus y1 equals mx, just taking mx1 to the other side, which gives xc as mx1 minus y1 by m. I'll just write this as x1 minus y1 by m. This is the x-intercept of the tangent. Now the distance QR is nothing but x-intercept minus x1, as you can see, basically the subtangent. So subtangent given by xc minus x1, that is my QR, or that is, you can say, the base of this right angle triangle. What does this give me? This basically gives me x1 minus y1 by m minus x1. So that is minus y1 by m. Okay, now substituting this in the Pythagorean step, where I'm using Pythagoras theorem, I get PR square is y1 square plus y1 by m whole square. Now I can take y1 common. I'll basically get y1 square 1 plus 1 by m square. Now if I take square root on both sides, I have PR, which is just y1 root 1 plus 1 by m square. This is the length of tangent. Length of tangent. There are a few different forms of this. So sometimes m is written as tan theta. Again, you know that tan theta is basically the slope of any line where theta is the angle it subtends from with the x-axis. So if I write m as tan theta, 1 by m is nothing but cot theta. If I say I write this as tan theta, m as also tan theta, I get y1 under root 1 plus 1 by m is 1 by tan theta, which is cot theta. So I have 1 plus cot square theta, which gives me 1 plus cot square theta is also an identity that is basically cosecant theta. So I have y1 under root cosecant square theta. So it's just y1 cosecant theta. So since we're taking a quantity, squaring and then putting an under root sign, that basically gives us a mod. So y1 mod cosecant theta is also the length of tangent. Where theta is the angle subtended by the line with the x-axis. So tan theta is the slope again, meant going back to that. Alright, so this is, I got the length of tangent. Length of subtangent is quite simple. Length of subtangent I already derived in this process. Length of subtangent was nothing but xc minus x1. This step. Length of subtangent was xc minus x1. So length of subtangent is just this minus y1 by m. Again, since it's length, I have to take a mod over here. So this is subtangent. Now, since I've used variable m right from the beginning, instead of dy by dx, I used variable m. If this m or slope of tangent I replaced with slope of normal and did the exact same set of steps, I basically get my length of normal and length of subnormal. So let's derive that. Exact same equation. I have y minus y1 equals now 1 minus 1 by m. Let's write the equation now. Y minus y1 equals minus 1 by m, where m is the slope of the tangent. So minus 1 by m is slope of the normal, gives x minus x1. So you need to understand how I can replace m with minus 1 by m in the set of steps that I just performed, and I will get not just length of normal or subnormal. I can do this for any line. If I'm given any line, the equation of any line, and I just adjusted the slope, that would give me a different line. Okay, but these set of steps would give me the length of that line as well as the length of its projection on the x-axis. Okay, so like how I got the length of the tangent and subtangent, I can get length of normal and subnormal. So let's proceed. Now going to the next step. I can use this a right angle triangle also. I have PQ. Let's take this point as say O. Now the new right angle triangle is PQO. I apply the Pythagoras theorem and proceed. I'll get the exact same result. But what I'm going to do is a quicker method. I'm basically going to replace m with minus 1 by m everywhere in the derivation of length of tangent and subtangent, and show you that I'll get the length of normal and subnormal. Okay. So finally what I've got as subtangent, basically xc minus x1. Over here in the final formula, I just need to replace m with minus 1 by m. So xc dash minus x1 is just minus y by minus 1 by m. Again, it's a mod because I'm taking length. So this is just my. Subnormal. This is the subnormal. And in this formula, y1 under root 1 plus 1 by m square, if I replace m with minus 1 by m, what do I get? I'll basically get PO from the diagram, which is equal to y1 under root 1 plus 1 by, now here I write minus 1 by m whole square, that goes to the numerator, so I'm just left with y1 under root 1 plus m square. So this is the length of normal. So y1 root 1 plus 1 by m square is length of tangent. y1 by m modulus is subtangent. my1 is basically length of subnormal, and y1 under root 1 plus m square, this term, is length of normal. Now m again I can write as tan theta, so I have basically 1 plus tan square theta in the under root sign, which is secant square theta. So this is nothing but y1 secant theta modulus. So let's write it down in terms of the parameter theta, which is the angle subtended by the tangent. Again, theta is the angle subtended by the tangent. I'll write down all four. So tangent is, remember these are lengths. Length of tangent is y1 cosecant theta, subtangent y1 cot theta, because I have y1 by m, normal is basically y1 secant theta, and subnormal is y1 tan theta. So these four are your lengths in terms of theta. I can just write it down in terms of m also. In terms of m, to recap, for length of tangent I get y1 under root 1 plus 1 by m square. For subtangent you just get y1 by m. For normal you get y1 root 1 plus m square, just a reciprocal, if you compare the length of tangent is just the reciprocal of the slope, that's all. And subnormal is m y1. It's good to have all the formula on your fingertips, so you don't have to derive it in the exam. Derivation is also quite simple though, but it's definitely recommended for you to remember all these formulae. There's 8 in total, 4 in terms of m and 4 in terms of angle theta. Let's just look at a question on the length of tangent, subtangent, normal, subnormal. Find the length of all 4 of these quantities to the curve xy is equal to c square at the point c comma c. You can check that c comma c satisfies this equation by putting the values of x and y as c. Okay, so if I put x and y as c, I get c into c, c square satisfies. So I'll just find the slope at point c comma c. I have xy is equal to c square. Let's differentiate this with respect to x to get the slope. This is equal to d of c square. Now by product rule this is just 1 into y plus x into dy by dx is equal to 0. So I have dy by dx is equal to minus y by x. Now just substitute the values of x and y as c comma c. Whatever the point is given, you will get dy by dx at c comma c is equal to minus c by c, which is minus 1. So this is the slope at the point c comma c. Now in all the 4 formulae for tangent, normal, subtangent, subnormal, I just have to substitute this, the value of m as minus 1. Yeah, let's look at all the 4 formulae. The very first one I have tangent, length of tangent is equal to y1 root 1 plus 1 by m square. So this one is equal to c under root 1 plus 1 by minus 1 square, that's just 1. So root 2 c. Similarly, length of normal is c under root 1 plus minus 1 square, that is also root 2c. And subtangent is just y1 by m mod. The minus sign that was there, it does not matter actually. I can put a minus sign also, but since it's a mod, the sign won't matter, which is just C, and subnormal, which is equal to my1, that will also be C. So the four values are root 2c, C and C. And if you look at the curve also, the curve is basically a hyperbola. Sorry, the curve is hyperbola, and the point C comma C is one of these 2 points. Basically these 2 points will be passing through the line y is equal to x. So at this point, if I draw the tangent and the normal is in fact just the line y is equal to x. At both points, if I just draw the tangent and the normal, this turns out this length and this length are equal, and this length and this length are just, so you can see that this length is just C, and similarly this one you'll also get a C. This point is it's like a symmetric point on the curve, and also the slope comes out to be 1 for the normal and -1 for the tangent.